Yeah, so yesterday we discussed about OSI layer, and the code to remember the 7 layers is please do not throw saucy pizza away or spicy pizza away. That way we can remember that, right? Let's see. Nag, can you tell me what is the difference between data link layer and network layer?
Data link and network layer.
Yes.
Not sure actually.
Sai Sri, your turn.
Yeah, so the data link layer is nothing but like transferring the data in the terms of like zeros and ones so that the system can understand, and the network layer is nothing but it uses the IP address and the like MAC address to transfer the data.
Okay, how does two systems talk inside the data link layer? Rajesh, question to you. How does two systems communicate inside the data link layer? How do they identify both of them?
Like in data link layer, like using the IP address or something.
Now, next, Managna, how do two systems communicate inside the data link layer?
Sorry, MAC address.
Yep, correct. Perfect.
Yeah, okay.
So I think next question, Managna, what is the difference between TCP and UDP?
So the TCP protocols, they need an acknowledgement if the packet is received on the other side or not, but UDP really don't care about the acknowledgement packets. It just processes real-time data.
Okay. Rishi, what is the three-way handshake in TCP?
Actually, the TCP needs acknowledgement, and is that what you're expecting, or?
Right, it needs an acknowledgement, that is correct, but there is a three-way handshake, right, in TCP. What is that? Next up, Aruna Suresh, what is a three-way handshake?
Yeah, first it sends the data packet and it sends the acknowledgement packet. Once it is received at the destination is going to send back an acknowledgement.
What is the first packet called?
Data packet. And sync packet. Sync packet.
Yes, synchronous packet, correct.
Yes.
Okay, next up, you, Varun. How does the user know what port to use when they are sending the data? How does the user know what port to use when they are sending the data?
So the firewall reads the content so that.
For example, I'm opening a web browser. I opened a web browser. I want to go to google.com. What port am I using?
IP based on IP address?
Shruti, what port am I using?
Oh, sorry, Ravi, this is my first class. Yesterday I was not there in the class, so I have no idea. Sorry.
Okay, that's fine. Go through the recording, Shruti. Thank you. Sudhir,
Yeah, sure.
what port am I using?
Port 80.
Why not 443?
I'm sorry, 443. Like HTTPS uses 443 port. HTTP use port 80.
Yep, because I want to make my transaction secure, I use port 443.
Yeah, yes, sir.
Why make discussion better దాని గురించి మీరు ఇప్పుడు దానికి డేట్ అవుతుంది ప్రశాంత్ తీసుకుని అట్లా అక్కడే కూర్చొని మెను అంత కన్ఫర్మ్ చేసుకుని వస్తారు ఇంకో
కాల్ చేశాను ఎప్పుడైతే నువ్వు వెళ్ళు
Hey guys, not sure where I'm getting it from. Okay, sorry, thank you. Yeah, I think that's all, guys. 10 minutes is done. Thank you for answering all the questions. You guys did a great job. I'm just tracking to understand where we can tighten up the screws, right? But you guys are doing a beautiful job. Thank you for that. Today we're going to talk about topologies. I know yesterday we talked about OSI. That's a day 2, right? But we were talking, we want to understand the core concepts a little bit, the movement, the movement between the packets, right? That's why we went with OSI. Before going to the topologies, I wanted to talk about TCP layer model. The TCP layer model is the short version of OSI model that is used to, for the network engineers, easily understand what's going on, right? So we don't care about, yesterday we talked about, we don't care about session layer and presentation layer. That's not our domain. There are other engineers who deal with it and fix that, right? So that's why the TCP layer model, again, the idea is same. To troubleshoot the issue, to understand and fix the issue faster, we divided the core concept of troubleshooting into multiple layers, right? So the TCP layer, TCP IP model does the same. Can someone tell me what are the 4 layers of TCP IP?
Physical layer, application layer, transport layer, and network layer.
Okay, anyone want to try again?
Application layer, internet layer, transport layer, and data link layer.
Okay, all right. So physical layer, data link layer, and they both combined it as a network layer. So they both combine into a network layer, and the network layer is called as internet layer here, and transport is transport, presentation, session, application. They all combine into one layer. So let's draw it out. Hold on. Okay. Click again. Okay. I wish I can have a trackpad. Oh my. And session. Anyways, so you understand physical data link, network transport layers, session presentation layer, right? So the physical layer and the data link layer, they both combined and call it as a network layer. Okay. The network is called as okay. Network layer is called internet layer, and the transport layer is called as transport layer. And these three combined and call it as application layer. So just for network engineers to make their lives easy, they named it as these layers, the transport layer, but the concept is same. When there is an issue, to troubleshoot it faster, to understand what's happening in the network, they call it as different names, right? So that's the 4 layers of transport. So maybe in the interview they're gonna ask, tell me what are the 4 layers of TCP/IP. Then you can tell these layers, right? So so that's about TCP layer. There is not much to discuss about it. It's a short version of OSI layer model. So now let's talk about the topologies. Let's take, I think 4, 5 topologies are there in the real time. But if you go through the books in the old
Details.
If you go back in the history, right, there are different models, but very rarely we're going to use those network topologies these days. When we talk about a star topology, a mesh topology, a ring topology, these are all old. No one are using right now. We're going to discuss that from an, I would say, theory point of view, but no one are using in the real time or in the real world in any of the corporate networks. So let's talk about a small home network first. And from the home network, we're going to go to a small branch with one, maybe let's take a small retail store, maybe a Macy's store, or let's say JCPenney, whatever retail stores. Just take that store as an example, look into the topology of that. Next up, we're going to look into a building with 3 floors, maybe an office building, maybe like 50 users, 100 users sitting in a building. How does their network connect? That's a topology 3. And the next up is data center. Data center is where, like, you see these big buildings, they build the servers. When you see racks and racks. When I mean rack, a closet which has a servers in it, that is called a rack. You see racks and racks of servers racking up for storing the data. For example, YouTube has all the videos, right? They have to store that amount of YouTube videos in a centralized place. So they build a data center where they can store all the data. So we're gonna look into topologies of maybe a YouTube data center. So we will look into all of that today. So first topology, home network. So in home network, what we will use in the homes, right? So in a home network, let's start with drawing it out. So there will be maybe 4 users. In a specific home, right? So maybe they all will have maybe 4 PCs. They all can have 4 phones. They have maybe like 2 iPads, maybe 1 printer in the house, maybe 1 Xbox, maybe 1 garage, ring doorbell connected to the Wi-Fi, like that, right? So these are all, maybe your smart TVs, right? Maybe 2 smart TVs, 1 on the down floor, 1 on the top floor, if you're using 2 floor, right? So all of these are like in your home or in my home, we have these kind of devices. We all pair them with our router, Wi-Fi router, right? So So this Wi-Fi router will be connected to what? A hard-coded jack in your system, in your home, sorry. So in your home, you will see an Ethernet jack where your router will be plugged in. You might have seen an yellow color cable coming from the wall outlet connecting to the Wi-Fi router. When you might have all purchased the Wi-Fi routers, or the installation guy will come to your home. They will give their own router to you. They will plug in up, they will set up. And then what you're gonna do is you're gonna go to your system, your laptop, you're gonna select your SSID. You, of course, you will have the access to this router. You're gonna put your username, password, and then you will log into that SSID. SSID is nothing but a specific VLAN or a specific name of the access point that you are accessing the signal from, right? And this wall jack goes from your wall jack. They will run a cable from your wall jack to all the way to their street router, which is connecting all of your houses into the street router. Like maybe my house, my neighbor's house, and the other neighbor's house, they all have wall jacks. They all will be connected to the street router with the cable. And from there, the street router will be connected to the centralized ISP service provider, whatever the location is. They're gonna run the cable, maybe like an dedicated link, or they're gonna use a transport between one ISP to the ISP, but we don't care about that for now. So in this topology, this is very simple, right? So you are using Wi-Fi. The Wi-Fi connects to the jack of, the router. The Wi-Fi router will be connected to the street router, and that goes to the ISP. So you are good. In this case, all of your laptops are wireless connected. But in few houses, we do hard-coded, right? All of your MacBooks or all of your laptops will have an Ethernet port, which can have an Ethernet RJ45 that can be plugged in. So from the jack itself, instead of the wireless Wi-Fi router, you can run a cable to your laptop and you can hard code it. You can use it with a cable. That is just like having an Ethernet connection to your laptop, and it's not Wi-Fi. If you use a Wi-Fi is like in the air, you are getting access out of it, right? But if you want to use a hard-coded cable from your wall mount, you can run a cable and directly plug into your laptop. You'll get the same access. From there, it goes to the street router and it goes to ISP. Okay. So this is a simple topology. Let's add a little bit, a layer to it, right? So in this same topology, let's say I want to have, let's do this. I want to have a firewall. That firewall can be plugged into the router, Wi-Fi router, and that Wi-Fi router can be plugged into the Ethernet jack. The wall mount that can go to the street router, right? Can anyone tell me why did I place the firewall here inside the house? Why did I not placed here? My question is, Wi-Fi router, firewall, jack, and then the ISP, right? So in my home, why did I place a firewall here instead of placing the firewall before the Ethernet jack? Any ideas like why did I place it here, or is it okay to place it here? I mean, I don't need any network answers, but logical thinking about it. Why do we need a firewall, and why did I place my firewall before the Wi-Fi router? Any guesses?
To avoid access of other people to our network.
When you mean other people,
Uh,
who are they?
who doesn't belong to our home network?
But those will be sitting here, right?
Yeah, yeah.
When they are coming in,
Mhm.
they're already accessing our network, right? But why did I place my firewall here?
Or to block to
For
block
security rules.
to s- uh, to block certain websites within our home network, maybe.
Well, even here I can block it, right? When I'm going here, I'm going out of my Wi-Fi, I can block it here and then go into the jack, right? Even I can block it here.
So I think yesterday you have mentioned about IP address. So considering that people can access using the same IP address, if we have kept the firewall in front of the Wi-Fi router, like between the user and the Wi-Fi router, there is no more connection directly to the Wi-Fi router.
Okay, so you are saying that I'm going to put the firewall to avoid the access to the internet?
No, not internet, like the data from stealing or accessing the data.
Okay, got it. But what I'm saying is, even if I put the firewall here, I'm going outside, I can still control my traffic going to the data and stop the data here. So the
As
thing
this is
is,
before the jack, so actually we are having a direct access between the user and the router. So there is
yes.
possibility for the user to connect with the router. So he will be in direct access with the other user, like with the other data without any layer in between.
Okay, so you're saying there is one more user here,
Yes.
and you wanted to block the communication between them inside the network.
Yes.
Okay. So the design that we are talking, the above design is inappropriate for a home network. The design that we talked about, the bottom, is appropriate to have a home network more secure, because we are protecting the data. Even though if you have two users, to communicate between them, you can route them via Wi-Fi router to the firewall and then come back to the other user. You can block the internal access via here as well. It doesn't mean that the Wi-Fi can make them communicate directly between them. You can make the Wi-Fi to act as a default gateway to your firewall, and you can still block them. So in a small network, always the firewall have to be your first hop reaching your network. I got two solutions, right? So Aruna said, to block external threats, we need a firewall, which is correct. And Rishi said, to block internal access, we need a firewall. That is also correct. But placing the firewall, the first hop will be more secure to protect our Wi-Fi router and also our internal users. That's why keeping a firewall outside is correct in a home design. So whenever you're designing a small office, if someone says like, hey guys, design a small network for us, always put a firewall before your Wi-Fi router connecting to the jack. That is more secure design than putting your firewall inside. Any questions there?
So can we hack the router?
You want to hack the router from inside?
No, not inside. As it's direct, we need not hack. We can directly like
Yeah,
do it
you're
because
a trusted user
as we
inside
are
the
the
network, right?
trusted user.
But when someone is trying to hack your Wi-Fi router, your firewall is blocking that hack. Okay, So that is a small home network. And the next thing is a small store. So in the store, what they will have. So maybe similarly, they will have multiple counters where you pay your bills. Let's say you purchased a perfume. There will be 2 counters. You can pay it here or you can pay it here, right? So there are 2 systems, or there might be 2 floors, 2 floor stores. But let's talk, there is a small store, maybe Bath and Beyond. So there is a small store. There are 2 systems, whether you can pay the counter here or you can pay the bill here, right? So these 2 systems should be communicating between them, and these 2 systems should be in the same network. So that's a small store, right? So in this case, what you're going to do, you're going to put a switch. Right? Because it's a small network, you don't need to have 2 separate networks. You're going to put a switch, cable them to the switch, and that switch can be connected to your Wi-Fi router, and that goes to the jack, and that goes to the ISP. Why do we need the switch here? Why cannot I just have a Wi-Fi router and make these 2 communicate? Why do I need a switch?
Because the system has to talk with each other within the network.
Can I not talk with my other system using a Wi-Fi router? Can I not do that?
What is that?
Without having this switch, can I not make these 2 systems communicate with a Wi-Fi router?
You can do that if that is connected to same network.
Right, but why do I need a switch? That's the question.
Maybe make easy for the connecting to machine, like 2 counters.
Yeah, you're so close. What is meant by easy? Faster. We want to make them communicate
connect faster, maybe.
We wanted to have one broadcast domain. Let's talk about broadcast domain a bit, right? Broadcast is a technical term again. Actually, I got an answer in the chat. Let's see. Actually, Wi-Fi sandwich is on a wide range and possibility of others to join and access. Yeah, in a sense, but I'm going in a different direction here. So I want to make these 2 counters in a same broadcast domain. Means that if I want to communicate this laptop to this laptop, when they are in the same broadcast domain, means the switch, whatever the frame that comes in, directly forward this to the PC2 if they're in the same domain, if they want to communicate. So broadcast is, let's say there is a PC that's connected to a switch, and there are, let's say there are switch ports, 2, 3, 4 ports. There is PC2, PC3, PC4. If I send the data to the switch can broadcast it, meaning like announce it to all the PCs in the same switch, because they are part of one broadcast domain. So whatever the data that comes in, it can send to all the PCs. That is a broadcast domain. Just think it like an FM radio. So the FM radio RJ will be sending that to the antenna, and you have an FM radio, I have an FM radio, and the other user has an FM radio. They broadcast it, so all of the radios will collect that data. So what is this antenna doing? It's broadcasting, right? Similarly, the switch is broadcasting whatever it comes to it. It will broadcast to all the connected machines. So it makes things faster. That's why you can put a switch there. But if they want to go to the internet, again, same story. They go to the Wi-Fi router, they go to the jack, they go to the ISP, go out. That's it. So that's a small store where you put a switch, right? understand that. Okay. Let's talk about two floors. Two floors. So there is a floor 1. So let's say this Bath and Beyond store is now in 2 floors. So we have more counters now. Maybe counter 1 is for kids. Counter 2 is for both adults, right? Or maybe home furniture, something like that, whatever it is. So there are two more counters in floor 1, floor 2. So for floor 1 and floor 2, you will put in the floor 1 for systems, you will put a switch. Similarly, for floor 2, you're gonna put a switch. So there are 2 ways. You can have Wi-Fi router here. You can have one more Wi-Fi router here. But this Wi-Fi router, because it's a big floor, it cannot broadcast that signal everywhere, right? So let's remove the Wi-Fi now. There is no chance of Wi-Fi sending because the store is big. There are multiple aisles in the store. The Wi-Fi access points cannot send the data to everywhere, right? So that's why we wanted to have we wanted to hard code this switch to a router, and that router will be connected to jack that goes to ISP. So there is a flaw in this design. What is that flaw?
One question. Yeah, I know what is a router. Physically, I have seen a router, but how will be a jack physically?
A jack is nothing but it's like a wire connected mounting from your home. So if you go to your router, your Wi-Fi router, see where it's connected to the wall mount. That is the jack.
Oh, okay. Okay. Yeah. Thank you.
Let's take a step back. What I was saying. So there is a flaw in this design. What is that flaw? What is the disadvantage of this design? When my company, when I'm extending my business to 2 floors, what is the flaw in this design? Anyone can tell?
The system in the first floor cannot connect directly with the second floor. It has to, everything should go through the router. Maybe I'm wrong.
Let's give it a chance to Manogna. Manogna, what is the flaw in the system? Any idea?
No, I'm still thinking.
Okay, what happens if the router go down?
So if the router goes down, there'll be no connection between the 2 systems, right? Like there'll be no data sharing or.
Yeah, correct. So both the floors are dependent on a single router. If that router go down, my entire network is gone. That is the flaw. But if this switch go down, these 2 systems, if you have a cable run to this system, you can have redundancy, right? And if you have systems running to this this switch, if even though this switch go down, you can have redundancy out from that system, right? So there is some redundancy there because you have one switch in each floor. That's why what they do is they do a full mesh topology. Full mesh means they bring out a full mesh, meaning, let's say there is floor 1, floor 2. So they connect to the switch. These both connect to the switch. And these switches will be connected to a distribution switch, or you can call it as an aggregation, distribution, whatever it is, the names, right? So this will connect to this switch. There will be another switch which will be connected to, or you can call it as a router 1. There is a router 2. I don't want to confuse you guys. Let's talk about routers only here. Router 1, router 2. This goes to this router, this goes to this router, this goes to this router. So there is a full mesh here. And that routers will be connecting to jack 1 or jack 2. And they both go to ISP, whatever your street is, right? So in this case, this is called multi-home network. What is multi-home? If one internet service provider go down, you have an option come via other one. If one router go down, you have another router. If one switch go down, you have another switch. So there is a chance of redundancy. There is a chance of high availability. What are the two terms? Redundancy. What is redundant? Redundant means there is an alter path. What is high availability? High availability means which is always available. So it's a very common terms used in IT that they're going to ask, is your network redundant? Then you have to understand that they are talking about, do you have two routers? Do you have a full mesh? Do you have two jack points? Do you have two internet connections? If they're talking about multi-homing, you have to understand that they are talking about the redundancy and they're talking about high availability, meaning if one router go down, do you have the backup router? That is what high availability means.
So don't we connect router 1 and router 2?
Why? Let's talk about why not and then talk about why. So what happens if we connect router 1 and router 2? I think it's not fair to ask you guys that question. Let me answer that. So there is a switch that connects to router 1. In this case, router 1 is connected to a router 2, and the router 2 connected to the switch. And what? We also have a switch. And this will be connected to this router, and this will be connected to this router. So we have a full mesh here, but we also have a loop here. So when the packet comes in of the switch 1, it may go to the router 1, and the router 1 will be connected to the router 2, and the router 2 will be connected to the switch. So we are creating a network loop here. So the packet is rotating between them, between the devices. There are ways to avoid it. There are ways to avoid these loops, but we are not there yet. That's why it's not connected the link between them. But if we connect that way, we are creating a network loop between the devices. To avoid that, there are protocols. In the switching, there is a spanning tree that will avoid the loop. In the routing, there is a concept called dynamic routing protocol. It can be an OSPF, it can be a BGP, it can be an EIGRP or ISIS. There are different protocols to avoid those loops, but they can be connected. But in this design, there is no value adding in extra cable between them, unless if we wanted to sync the configuration between them. If we want to sync whatever we wanted to do on the router one, we want to sync between them, then we need to have a cable. If not, the design what we built is already highly available. We don't want that extra link, which will cause us the loop. Are you guys following me, or did I move too fast on that?
No.
Oh, it's
We are
clear.
able-
Yeah.
Okay, cool. Okay, so quick time check, 9:46. Okay, I mean 10:46. Okay, guys, let's talk about the last of all. I think we talked about a small home. We talked about a small store, and then we talked about a multiple floor store. And then we're gonna talk about maybe like a data center, right? So the data center design is a core. Well, there are two data center designs. Let's talk about designs until 2014. Let's talk about designs after 2014. So before 2014, the data centers look like this. 2014, or maybe 2015. I'm not exactly sure about the dates, guys. Just think about like before 2015 or something. We used to have one cloud, which is ISP. Like this is just internet, right? So that internet will be connecting to router 1, router 2. These are called edge routers because they are acting as edge of the network. And these routers will be connected to distribution switches. This is the distribution switch of floor 1. And that's why I'm making as floor 1. This is floor 2. This is floor 3. Let's say there are 4 floors in the data center. Floor 3 and floor 4. So what I'm going to do is I'm going to do a full mesh. And after the floor, there is an access layer inside each floor. Maybe there are like 4 counters or four servers, PCs, servers, office spaces, everything, right? They all will be connected to the access layer switches, and they all will be connected to floor 1 switch. That will be connected to PCs. This is all PCs, users, whatever they are connected to. Similarly, on the floor 2, again switches. These are called access layer switches. These are all PCs, laptops, whatever they are connecting on that floor. They will be connected to floor 2 distribution switch. And this PC will have connection of this one or this one, right? So yeah, similarly floor 3, floor 4. So what is the reason behind this design is, this design is highly available. This design is redundant. So inside the floor 1, you're gonna keep one more distribution switch, which is called redundant switch inside the same floor 1, and you can make this as a fully mesh here, right? So inside that floor 1, you can have 2 switches there, and you can make this as redundant here in the full mesh. Similarly, in the floor 2, you can put one more floor 2 switch, and you can have full mesh, and that floor 2 switch will have equal connections to the router. So even if one switch go down, this PC will have connection to the other switch, and that will go to the floor, and it will go to the router, and it will go to the internet. So because you are sitting in your home, you wanted to see a YouTube video. Let's say this is a YouTube data center. And when you want to see a video, you will make that call to the ISP. The ISP will send that to the YouTube router. The YouTube router will see, okay, he is trying to watch maybe Stranger Things. That router will see, okay, Stranger Things resolves to this server IP address. So that lives in this data server. It connects to that data server, and that data will be sent to the back to this switch. That sends to the router, that sends to the ISP, and the ISP will send the data to you, and then you're gonna stream the Stranger Things on your home PC, right? So that's how the data centers are built. Let's say this switch went down, but still you can still watch your content because these servers are highly available. I mean, these switches are highly available. You still have connection to your server via this switch. Let's say this switch went down in floor 1. Still you have connection. You can come via router 1. You can go to floor switch 2 that goes to this, any of the switch, and go to the server. Let's say this router went down. You can still have the ISP connecting to the router 2 that goes to floor 1, comes and goes. So whichever device went down, we still have a redundancy path to go to that server to get the data that you wanted. That's why people used to use this design. This layer is called core layer. This layer is called distribution layer. This layer is called access layer. And that's where we'll be connecting to the PCs. I mean, the servers or PCs, whatever, whichever the content that you want to get from the data center. This is how the data centers used to be. Any questions here?
In this diagram, when you say PC, it is multiple PCs, right? Not just one.
Not just one, multiple, no. Like thousands of PCs. We're not talking about one.
Oh,
thousands of servers, yes. Okay. Lakshmi, so quiet. Can you tell me what are the 3 layers of the data center? I think, Lakshmi, you're talking on mute, or you're trying to figure out your mute button?
No. Physical layer, data link layers.
I'm asking what are the 3 layers of the data center topology that we just discussed?
Store topology, net topology.
Surprised. Okay, let's talk. Hari, what are the 3 layers we just discussed?
Hold on, like I think I just forgot, like I heard, but I.
Okay, Ritik Tota, what are the 3 layers?
Those are core layer, distribution layer, and access layer.
Okay. Okay, that's good. That's good, Hari. Thank you. Lakshmi, I need a little bit more attention, please. I want you to be more attentive. Next up, let's talk about. Yeah, before we move on, Lakshmi, what are the 3 layers that we just discussed?
Core layer, a distribution layer, and access layer.
Thank you. Okay, So what is the problem with this design, right? So the problem is, this is fine, this is all good. When someone is in the home, they can access the data. But the problem is, because of their intercommunication between the servers, like for example, this server, this PC want to communicate on this PC, they cannot directly switch between them. They have to go to this switch, and this switch have to go to the router, and the router will send the data back to the PC here in this grid. If they want to communicate between them, we are, let's try to change the color. Maybe 1 sec. Okay. So for example, if this PC want to talk to this PC, right? So it has to go to this switch or any of the switch, that has to go to this switch, that has to go to this router, and it has to come all the way back here. So this is unnecessary flow of traffic directly over here, which is not feasible because the data centers got bigger and bigger. Social media came, people started to use more data. So this is not feasible because the intercommunication is getting too much delayed in the data center. That's why they moved an architecture called spine and leaf architecture. Spine and leaf architecture. What does this do? What does this do is, it has spines. In each floor, there will be one spine. Floor 1, floor 2, floor 3, floor 4. We're talking about floor 4, right? 4 floors, right? So inside the floor of the switch 1, switch 2, which is called leaf 1, leaf 2, leaf 3, leaf 4. So this leaf 1 will be connected to floor 1 switch, floor 2 switch, floor 3 switch, floor 4 switch. Similarly, let's say this leaf in this floor 2, the leaf switch is nothing but the access layer switch there, right? So that will be connected to this switch, this switch, this switch, switch. So it is called again a fully mesh. If this switch go down, it has 3 other switches to go out. Similarly, if this switch go down, you have 3 other paths to go out, right? So every floor switch will have the connection to all the leaves in that floor, and that will be connected to the servers. And then these switches are connected to routers So earlier we talked about a problem, right? So if there is a PC here, if it wants to communicate the PC with here, it has to go to all the way here and then come back and talk to it because the layer 3 lives here. Because they are in 2 different networks. If they're in the same network, that's fine. They can directly talk with a switch. The switch will send that to the data to the other PC because they are in the same network. They can do with the MAC address. But if they're in the 2 different networks, they still have to go to a layer 3 device like a router, right? That's why they did these as the layer 3 switches. So now, if this PC wants to communicate with this PC, they don't have to go all the way to the router. They can directly go to the layer 3 switch and then come back and then talk directly. So they avoided going all the way back to the router with this leaf and spine topology. They moved the layer 3 from here. They put the layer 3 to here. On the spines, you can have your layer 3 and you can have intercommunication inside with, there are different protocols to do it. That is not covered in CCNA. It is covered in the data center track. This is not this topology is not in CCNA syllabus, but this is what we use in the real time. I mean, in maybe 2 months, you all will do the job, right? So if you go there, you will see these kind of designs. That's why I'm talking about this. But in the CCNA, they don't talk about this design. They don't even talk about this design. They just talk about this design. But if you go to the network, you will not see this design because you all will be working in MNCs, corporate networks, which they will not use this small store. But anyways, let's stop there. It's already time. I'm gonna pause there. I'm gonna repeat whatever I said today, just on a high level. So we talked about TCP IP layer model, which is a short version of OSI model. It is representing 4 layers. Physical and data link is mapped to network layer. Network layer is mapped as internet layer. Transport layer is same as transport layer. Session, presentation, application are mapped to application layer. So that's about the TCP IP model. And the next we discussed about topologies. One is a small office, I mean a small home or an apartment, which will have a Wi-Fi router that will be connected to the jack, that will be connected to the street router, that will be connected to the ISP, whatever it is. That's a simple flow. Next thing we discussed about, we added a switch to make them fasterly communicate in the same office or a same store. We added a switch. But when the business improved, we went with multiple floors. So we added 2 switches. We put a router. For redundancy, we added 1 more router. And then we have the jacks and we send them to 2 ISPs. We wanted to do multi-homing. If we don't have the money to pay with 2 ISPs, we can just connect both jacks into 1 ISP and just pay for 1 internet bill. That's it. And if your internet go down, that's it. The store lost the connectivity. But if you have the money, you have to invest in 2 ISPs. You have to pay for 2 internet bills. Next up, we went with a bigger design with access layer, distribution layer, core layer, where we separated our network into multiple floors. But because it's a data center, there are a lot of machines in the data center. We wanted to have highly available and a 24/7 available network, which can be redundant and highly available. So that we went with. But the flaw is the intercommunication inside the same data center is slow and it's getting too much traffic on the core. We wanted to spread that. So we went with spine and leaf. So here in the spines, the layer 3 is moved to all the spines. I'm sorry, the layer 3 is moved to all the spines. So any PC can communicate with other PC or other server using any of the spine. It can talk via spine 1 or it can talk via spine 4. So we are sharing the load across all the spines and we moved the layer 3 directly to the spines. So that's a short version of it, the short summary of it. I'm gonna stop there. I'm gonna give you 10 minutes to ask the questions.
Yeah. Yesterday, you were talking about a lot of links, right, to study. Can you please repeat that one more time so that I can write?
They are in the channel, aren't they?
Channel.
Yeah, maybe it got lost with the messages. Let me do one thing. Let me take it as a follow-up. I'm going to paste those links again. So it will be there. I'm going to start that message as well. I'm going to do that today before the next class.
Okay. Because I joined very late, I think so. I don't see all the messages.
I get that. Thank you. We'll do that.
Hey Ravi, if you don't mind, could you repeat that the span and leaf thing I don't understand because in near the spine and leaf connections.
Sure, let me do that.
Yeah.
So you understand why we went to the spine leaf design, right? You understand that point, right?
Yes, yes.
Yeah. So what we did is when we have let's say there are two switches here, and there is one PC. These are leaf 1. This is leaf 2. In the floor 3, there is leaf 3, and there is leaf 4. This is a switch. Leaf is nothing but an access switch. So they all will be connected to, let's say, spine 1 and spine 2. There are only 2 floors now, so I'm just doing 2 spines, right? So spine 1. So the PC1 is connected to leaf 1, and it's want to talk to PC that is connected to leaf 3. The layer 3 is here, L3 switch. Let's say this is 10.1.1.1. This is 11.1.1.1. So if this PC want to talk to this PC, it goes to leaf 1. Now it has 4 paths. It can choose spine 1, or there are 2 paths. It can choose spine 1 or can choose spine 2. This is called equal cost multipath, ECMP, because there are multiple paths to go to the destination. So either I can choose spine 1 path or I can choose spine 2 path. After, let's say, I picked spine 1. So to reach PC, it can go from spine 1 to the leaf 3, and it can go to the PC. So in this design, we are not moving all the way to the router to come back to the PC. We are reducing the number of hops, and also we are adding more resistance, because let's say there is spine 3 and spine 4. You have 4 ways. You can go with spine 1, or you can go to spine 2, or you can go to spine 3 and come back to leaf 3, or you can go to spine 4 and come back to leaf 4. So you're adding more capacity to your core design because you are having more spines. You're not relying on routers only, which are 2. Make sense?
Yeah. I guess Ravi got it.
In the previous thing, like previous network, the data center network, it went through lot of layers, right? That's why we go to spine leaf model. But here also there are multiple layers. I didn't get it. Oh, instead of broadcasting to all the switches,
Well,
does it choose a path?
Yeah, every packet will use a single path. It does not broadcast every switch. It will choose a single path because it's a layer 3 device. It's not a layer 2 device anymore.
Okay. Got it. Yeah, can you just give me the expansion for ECMP again, please?
It's equal cost multipath.
Thank you.
Yeah, good call. If you join on your iPad or a Zoom user or someone else, can you please try to rename so that we understand who joined? Rishi is helping me to track who is joining and who is not. So it will be easy for us to understand who is joining and who is not. Please do that. So tomorrow we're going to discuss about the IP addressing, IP spacing, how do we separate the IPs, how do we create the subnets, like that. That will be tomorrow topic. So today we discussed about the topologies, right? So just try to draw these topologies by yourself. That will be a grateful help for you guys, that you don't forget about them. So even if you go to a job, you will relate those topologies in your job for sure, because every data center, every network follows one way or the other. So just go through them, draw your own topologies, try to figure it out. I know there are 15, 16 people. I cannot track everyone, but I'll try my best to assign some work so that you guys can interact and learn something out of it. I don't want you guys to waste your time. If you don't understand something, I'm sure it's not your fault. It's something that I'm missing on my side. That's why I want you to put some effort to learn from your side as well. If you learn something by yourself, you will never forget. But if I keep on saying again and again, there's a chance that you might miss it. So that's why do your due diligence and do your homework. Try to draw your own diagrams. And yeah, we'll figure it out what we're going to do about the assignments and the follow-ups for this week. Maybe I'm going to tell that on Thursday. So yeah, that's it for today. Any questions you guys can ask, or you guys are free to drop.
Thank you, sir. It's a very nice session again. Thank you.
Yep, thank you.
Thanks, Anna.
Thank you, Rishi.
No, actually, ఇద్దరమే ఉన్నాం కాల్లో.
One second, Rishi. Let me stop the recording. 1 second.
Yeah.